Did you guys see my new cup?
Oh, cool. What you
Yeah.
got on there?
So I'm trying to learn my eons and epochs and periods. So on this cup, it has the Paleozoic, the Mesozoic, the Cenozoic. And as I take sips, I look at how far within time I've gone. So currently we are in the Holocene. Is that correct?
That is correct. Well, Gavin, is it correct?
Well, Graham, this is a contentious point. I feel like we should talk about this today, shouldn't we?
I think we should. So
We,
today we're
we can get to it a little later.
That's
that's
correct.
great. But
I
today,
actually got this cup from the museum store. I don't think we have any in stock now, but I'll put a link in the comments for everyone who, if you want to explore the nature goodies that we've gotten there, you can take it. But I pulled this out today because we are going to be talking about geologic time, are we not?
We are, Marisa. Today is geologic time, and specifically the events on the geologic timeline. So I think that cup is pretty good just to make sure that we're going along right.
I'll
right.
keep track of where you guys are at on it. Let you know if you've made any mistakes.
very good. Make sure that we're keeping on the timeline proper.
Okay. And then also, yeah, for everyone joining us today, if you have any questions along the way, you can write them in the comments. And maybe see if you remember any geologic eras or epochs. See if you can write them down in the comments. Test yourself a little bit before we get too deep into this. And if you have a rock you'd like identified, there's a link in the description, and you can go there, put your picture there, and we'll take a look at it at the end.
Great. Well, what do you say we dive back in time?
Sounds great, Graham. Let's get in our time machine and go back in geologic time.
Oh, love So today, there's so much great stuff happening in Earth's history. We could spend a week on a Zoom call like this, just talking about all the wonderful things in Earth history. But today we're gonna have to trim it down to the greatest hits. Will that be all right, Gavin?
Oh, that sounds great, Graham. A couple of good ones.
Great. Well, I think the best place to start is really a key moment in the history, not of the Earth, but of the study of geology. So we're going to go back to 1788 to Sicker Point in eastern Scotland, along the east coast of Scotland. Gavin, what happens on this momentous occasion?
Well, Graham, this is the birthplace of geology. So when our friends James Hutton and John Playfair are walking along Sicker Point, Scotland, 1788, the study of geology is born. These guys are looking at these rocks, and they find some really interesting things that basically blow their mind, right, Graham? What do they find?
That's right. So they're looking on the exact same picture we've got up here, the same thing that we've got for our background here. If only we were together in Sicker Point today, Gavin. But virtually we'll have to do. But what they see here is they see these mudstones that are in straight lines going away from them. So that's everything below that blue line that I put on there to give us a little cheat to help guide the eye. So there's those mudstones going going out as the eye sees, and then they're cut, they're stopped and interrupted, and on top of them are these much younger red sandstones. So Gavin, how could that have possibly happened?
Well, Graham, first of all, everybody should remember back to our Rockin pop-up about sedimentary rocks, because these are sedimentary beds, and the sedimentary beds below that line you drew for us must have been tilted and then eroded off. And then the sedimentary beds above this blue line are then deposited later on top of them. And so what James Hutton and John Playfair notice is that there must be a ton of time missing where you've drawn this blue line. And that pretty much just blows their minds. They realize that Earth history is really, really long.
That's right. And so they've got a couple of great lines here. My favorite of these is John Playfair's, where he says, "The mind seemed to grow giddy by looking so far into the abyss of time. it's almost overwhelming just how vast geologic time is. The world is so old.
That's right, Graham. And this is a pretty profound idea in the history of science when humans realize that they are but a blip in the timeline of the Earth's history that goes back really, really far. And so, Graham, how do geologists think about time?
Yeah, so that's such a good point. And, you know, what we do is we use our tools of geology to help go back in time, to use these rocks as our time machine. And we can go to all sorts of places on Earth and catch glimpses of rocks that come from certain periods of time. And so, yeah, how can we use those rocks, Gavin?
Well, Graham, if you can imagine that any place on Earth, you're looking at pretty distinctive different rocks. And depending on where you are, those rocks are maybe older or younger. And so depending on where you are, you're at a different point in the timeline of Earth's history. A lot like what you have here, like a history book, right? Each rock you find in nature is putting you at a different page of that history book.
That's right. Unfortunately, our geologic history book has pages missing all over the place. Like we saw at Sicker Point, right? There's a bunch of time missing in there. We don't just have a continuous story of the geologic history there. And why don't we have that history, Gavin?
Well, Graham, if every single rock that ever existed still existed today, well, there would be a lot of rocks on Earth. And what happens is that you weather them away. You destroy rocks and you make new rocks all the time. And so parts of the rock record, what we call it, those pages in the history book, are all the time being destroyed to make new pages of that history book, right?
Oh my goodness. At first I was sad for all that missing rock record, but when you described it like that, it keeps geology exciting. And so it's always keeping the earth fresh and there's always a new mystery to solve. What a fortunate conundrum we find ourselves in.
That's right.
So Gavin, as geologists then, we're left with this incomplete story. And so we need a tool to connect different things in time because we can't just follow time continuously. So tell us a little bit about this tool.
Yes, Graham. Okay, so basically all the knowledge geologists accrue by studying the rocks, they have to put somewhere. So they create a timeline. That's the geologic timescale. And so you have this up here on the right, the geologic timescale. And what people in the audience may notice is that there are some pretty large divisions, so divisions of time that consists of a lot of time, and then we get really, really short time scales as well. So we go from really large divisions, which are the eons and the eras. So eons are about 1 billion years of time, eras hundreds of millions, and we can get way more specific down to epochs and ages, which are divisions of time that are more specific, smaller divisions in time, right, Graham?
That's right. And so everyone out there viewing, you may not have known this, but you will now. We are living in the Phanerozoic eon, in the Cenozoic era, the Quaternary period, and the Holocene epoch, or epoch. Different folks pronounce it different ways. But that Holocene is a little bit of a contentious one, right?
That's right, Graham.
At the beginning of this.
That's right. And so we'll get to that. But one thing I just wanted to add here too is that the divisions in time and the timeline goes from the present all the way back to 4.5 billion years. And so if you think about human time as, humans popped up, 1 million or so years ago, that is just a blip in what is a really long-term record of geologic time.
That's right. And if we zoom in, we can find our period and our epoch right here up in this far upper left-hand corner of this time scale. And we've got all this time stretching out behind it, going all the way back to the Archean and Hadean eons of Earth's history. So there's a lot of time there, but we'll just go through some of the hits today. How does that sound?
That sounds great, Graham, because really, each one of these divisions in time oftentimes corresponds to something that happened that changed the Earth. So the divisions that we're going to talk about today are the ones that changed the Earth in some of the biggest ways, some of the biggest changes.
Great. Well, let's start with one that's very near and dear to my heart and also very near to us in time. Let's jump back to the last 2.5 million years, the Pleistocene Epoch. Gavin, what's happening on Earth during this period of time?
Well, Graham, this is a pretty chilly period. It's the Ice Age. And so 2.5 million years ago in Earth's history, something changed about how the Earth is getting energy from the sun that has to do with its orbit. And it made Earth's climate colder. And what happens in between 2.5 million years and 10,000 years is that we go in and out of ice ages. So we go from cold glacial periods to warmer interglacial periods and back.
Wow. And so it's almost like they're almost like our seasons, right? We've got a chilly winter and then a warm summer, but these are happening over hundreds of 100,000 years at a time. And so because it gets so cold for so long, huge ice sheets grow over all of northern North America. So all of Canada and a lot of the northern states of the US are just covered under a huge sheet of ice. You get the same thing up over northern Europe and northern Asia. A lot of the Earth just gets kind of swallowed up in ice, and then it kind of melts away. And so down just below that map and below the picture of those lovely Pleistocene megafauna, we see these sort of lumpy glacial terrains right outside of that ice sheet. We call those eskers or drumlins, but we see the same sorts of things all over the northern US. That picture where it's snowy is from my home state, Wisconsin, and that other big lump where it's kind of zoomed in on it and it's beautiful and green, that's from Gavin's home state of New York. We are proud to say that we come from states that were once, fully glaciated during the Pleistocene.
That's right, Graham. And I'm glad you put these on here because this is a good point. Like, the fact that Earth is cold and it has ice sheets doesn't mean that we're adding or subtracting necessarily any rocks from the rock record. So how do geologists know that this happened? Well, we see evidence on the surface in these drumlins and all kinds of different evidence that the ice sheets left behind.
That's right. So we can think of these drumlins, even though they're not rocks in the same way that we look at Sicker Point, but they're also recording that really important chapter of Earth's history.
That's right.
All right. Well, I'm getting a little cold. Would you say we heat things up a bit with some warm mass extinctions?
Ah, yes, mass extinction. Some of the warmest times in Earth's history.
Certainly.
And sometimes too warm if you ask the dinosaurs.
Absolutely. And so the mass extinction we know the best is probably the Cretaceous Paleogene, or as we geologists like to say for short, the KPG, that happened 66 million years ago. Gavin, this is not a fun time to be around. What's going on Earth at this time?
That's right. So before this, dinosaurs walk on the Earth, and then so this is the famous one because it kills the dinosaurs. And the thing that happens on Earth is sort of a double whammy. So the first whammy, the first thing that makes it hard to be living on Earth at this time is a huge meteorite impact. And this meteorite is impacting off the coast of what is now Mexico. We call it the Chicxulub impact. And that impact changed the Earth's climate and changed the dynamics of the Earth enough that it made it really, really hard to be alive. And that's one part of the mass extinction. But now scientists are coming to know that there was another whammy in there. There's something else that made it hard to live too, Graham. What was that?
So right around, probably even a little bit before that meteorite hit Earth, there was this huge volcano field over in India that we call the Deccan Traps, or the Deccan Traps. And here, we're not just talking about one mountain that's spewing lava out the top of it like we sort of think of when we think about Hawaii. No, this is a huge area, hundreds of miles across, that is just pumping out not only lava, but volcanic gases full of nasty things like like sulfur, sulfuric acid, and all sorts of other stuff that get up into the atmosphere and make Earth a much less pleasant place to live. And so a lot of changes going on there. And of course, in the midst of that, Chicxulub comes and there's a huge rapid change in climate, and it makes it really hard for all the food chains and all the the ecosystems to keep supporting themselves, and they collapse out. But if we thought that was bad, Gavin, things were even worse at the end of the Permian. What was happening then?
That's right, Graham. So the KPG, or the Cretaceous mass extinction, that is really famous, it's probably the most famous, but it's not the largest mass extinction in Earth's history. That goes to the Permian Triassic mass extinction, which you point out is 251 million years ago. And this is a time where you also have trap eruptions, large amounts of lava being spewed out over the surface of the Earth, but this time in Siberia, in a place called the Siberian traps. And so much like what happens when you have the Deccan traps at 65 million years ago, these are changing Earth's climate so much so that 90% of the life on Earth and in Earth's oceans are becoming extinct at that point. So this is killing off a large majority of the life on Earth, right, Graham?
That's right. And there's something important to note here that I think we need to take as a cautionary tale for us, is that these mass extinctions, it wasn't the volcanic eruption, it wasn't the meteorite impact itself, it was the changes in climate that came along with these, that were driven by these, that made the world so inhospitable. So it's an important thing for us to keep in mind in the context of a changing climate. Not to say that exactly these same things will happen, but that these are the things that make Earth a challenging place to be. Yeah, I think that's all I want to say on that.
Yeah. And Graham, one other thing, just while we're on that note, is that you're right. It's not a single day that's killing the dinosaurs. It's not a single day that's killing things in the Permian. It's changes that humans would take as long-term changes. These mass extinctions are events that take place over 100,000 years, but we put them on a single point on the timeline of Earth's history because, that amount of time in geologic time is short compared to the 4.5 billion year record. But these things are changes on tens to hundreds of thousands of years that are killing a lot of species.
Yeah, that's such an important thing to recognize, that geologic, we often try and think about just points in time, but these are big ongoing global processes, and nothing ever just happens in an instant on Earth, or at least the biggest changes on Earth take some time to fully go into effect. But Gavin, these warm climates have me sweating. What do you say we cool things down a little?
We're going back to a cold time in Earth's history.
Much better.
Yes. So what's happening at 720 to 635 million years ago, Graham?
We are in a different period of Earth's history now. We're in the Cryogenian period. And you know me, I love to unpack the word. So this cryo, this I think is a Greek root for ice. And so this is an icy period. And we talked about the ice ages when parts of the Earth were covered in ice. But this is kind of a whole different mashed potato. Gavin, tell me what's going on right now.
That's right. So if you look at the picture on the right that you put here, Graham, it's not just some of the continents. It's not just all of the continents that are covered in ice. The whole Earth, or at least the vast majority of Earth, is covered in ice during the Cryogenian period. And people who discovered this call it the snowball Earth. And so you might imagine that it's actually really hard to get the Earth to be fully covered in ice, and it's really hard to get it out of that period when it is fully covered in ice. So this is a time where you have vast changes on Earth because basically none of the normal atmospheric exchanges that you get with any of the Earth or the oceans are happening, right, Graham? So what does this look like in the rock record?
Yeah, so this is great. So what you're doing is the Earth, or what's happening on Earth, is because we're sealing off the oceans, we have these really cool sort of bottled up chemical experiments going on in those oceans. And so for the folks who tuned in last week, I'm sure they'll be excited to hear that we get these really neat chemical sedimentary rocks. So as this ocean is sealed up, we build up a bunch of certain types of chemicals. And when we suddenly release the oceans and open them up, that drives them to precipitate out, because they can only form when the oceans are sealed up. So that helps us make things like a bunch of carbonate rocks, these chemical precipitates that are, hundreds of feet thick that just really rapidly show up in these ocean deposits. We'll see those going right on top of glacial deposits. And then right in the middle of the screen here, Gavin, there's something really neat that's also, forming from that, but it's a little bit different. These are banded iron formations. So these things are made of mostly iron, a little bit of some other stuff, sometimes some some chert, sort of siliceous ooze material. But Gavin, why is it so red? They're really striking.
Well, these things are red, just like you might think of something that's rusting, right, Graham? This is basically rust in the geologic record. You have a ton of metal being deposited, and that metal is being oxidized and it's forming rust. So you get these huge bands of these banded iron formations deposited after the Cryogenian, because you go from not much oxygen on the Earth's surface because it's covered by ice to rapidly oxygenating those oceans and getting these thick banded iron formations.
Remarkable. Absolutely incredible. So this must have been a pretty tough time to be around on Earth, and yet life was around before this, right? Life survived through this, isn't that right?
That's right. We had life before then, and we obviously have life after then. So life on Earth is pretty remarkably tenacious, right, Graham?
That's great. So I think for our next step, we should give a shout out to life, because life has been sticking around since 3.5 billion years ago, and so that's quite a bold claim. And I wasn't there 3.5 billion years ago. So how do we know that there were critters on Earth at that time?
Well, Graham, I like that you shout out to life, and I like that you shout out to this life. These are microbes and microbial mats, to be more specific. And so I think we should throw a 3.5 billion year old birthday party for the microbes that actually still exist today, because those are some persistent life. So you asked a question, how do we know that it was around? And we know it because we find evidence for it in the rock record. Literally fossilized microbes that look a lot like some of the microbes that we see in this top right picture, which is actually around today. It can't be the same thing, right, Graham?
Well, so I'm not going to tell you that they're the same cells, but they're really similar. These microorganisms, these little bacterial dudes, have been doing the same thing, growing in shallow water, making these boogery mats that they sort of build up and collect sediment in through time. They've been doing kind of the same thing for just about 3.5 billion years. And so they found a way to survive that works pretty well for them. You got to hand it to them, Gavin. They're clever.
That's right. And so we see these things called stromatolites, which are these bulbous microbial mats all throughout the rock record, from 3.5 billion years to the Cambrian all the way up to today. So they're remarkable.
That's right. And this picture comes from a very cool spot in Australia, Shark Bay, where you can find some of these. We think, dinosaurs were old. Well, these things beat them by another 3.2 billion years. It's incredible.
Incredible.
But just as life began at some point, we only know how, that it was at least 3.5 billion years ago. But what we actually know even better is how old the Earth is. And so we can't look to one spot on Earth to determine when the Earth formed. We need to look to meteorites. And we can go into that a little bit more next week about how those have been used. But Gavin, how did the Earth form? Paint me a picture. I'm curious to hear how it all came together.
Oh man, Graham. So the Earth formed when the solar system formed. And the beginning of that formation is in this nebula, this dust cloud in space. And there, you could think of this dust cloud as gas and dust particulates. And something happened that pulls all of that dust together. And that dust starts building small rocks and then big rocks and then planet-sized rocks. And one of those planets that it forms is Earth. And so you have this picture here on the left, on the bottom left, Graham, of this really hot looking ball of what looks like melted rock and rocks coming together. What's happening there?
Gavin, I love that description, just like poetry. And this leads up to the, this really important moment in the history of Earth and our solar system. We geologists and our friends, planetary scientists, we call it accretion. So accretion is this process of small things that are coming together to form a bigger thing. Really important process here is gravity. There's more than just gravity going on here, but eventually these things get big enough that gravity starts holding them together. And then once they're the size of the Earth, they're big enough that their gravity can start holding all sorts of things on them, not just the rocks, but the atmospheres and critters like us.
That's right, Graham. And so you start off as pretty much a molten ball of lava, right? Earth starts as a magma ocean.
Yeah, and that's pretty remarkable to think that we go from basically a rock soup to an Earth that's covered in mountains and oceans and trees and plants and 3 billion-year-old microbe lineages and weird things that walk around on 2 legs like us.
That's right, Graham. And so next week we'll talk about how we know the age of it, right?
Mm-hmm. But before we sign off for today, we promised we'd talk about it, and here we are. This is the Anthropocene Epoch. And so, Gavin, I thought we were in the Holocene. What's this Anthropocene hullabaloo?
Well, if you asked me and I didn't know, I would be like, this is just some more human hubris. Of course, humans are going to say that now that humans are around, the Earth must be in a different period or a different epoch. But the thing is that humans actually make some really big changes so big that we can, if you imagine that looking back 1 billion years from now, we could probably see it in the rock record, right, Graham?
Yeah, that's right. But where we put our finger on it, I think, is the thing that geologists tend to debate the most, because how big of a change that humans make is big enough to say that we're really changing the Earth system in a serious way?
It's a good question, Graham. And so you have here 12,000 years ago. What's going on 12,000 years ago? So that's the dawn of agriculture, right?
That's right. And this is a time when folks start planting things. And as they get more clever for planting things and raising crops and livestock, they also start building irrigation systems. They start diverting rivers. They start changing the way water flows over the Earth's surface and how the landscapes evolve. So that's one of the contenders for the beginning of the Anthropocene. Around 12 to 10,000 years ago, when those first irrigation systems pop up. We also see some smokestacks here. What's going on there?
This is a good question, Graham. So if you think about agriculture, the Earth would probably not really feel that. But the first change that humans make that is lasting is the Industrial Revolution. And so the Industrial Revolution is when we start burning fuel and using all kinds of the Earth's resources to make a more modern, technologically advanced society. And that's when things start to really change, right, Graham? As we burn fossil fuels, we're changing the atmosphere, right?
That's right. And so in a way, all this fossil fuel burning, it's actually causing this big climate system shift that is, not yet as extreme as some of those, big mass extinctions in history, but it's kind of a similar process. We're taking carbon that was stored deep in the Earth and rocks and releasing it to the atmosphere, and it's causing a dramatic shift in the climate here, the likes of which we haven't seen for tens of millions of years. But there's one other contender for the start of the Anthropocene that I think is pretty neat. And that's with that big mushroom cloud at the bottom of the screen. Gavin, what happened 75 years ago that where humans made a big mark in a big way in the Earth history?
Well, Graham, the mushroom cloud tells me that it's the first nuclear reactions. And a lot of scientists have been talking about the first nuclear reactions being where we should put the line of the Anthropocene. And that's because we are actually doing something called nucleosynthesis. We are making new atoms when we have a nuclear reaction. And that's something that we can see in the rock record. We actually see a line in the rock record that points to the first nuclear reactions.
Wow, that's pretty remarkable. Yeah, so it's in 1945, the Trinity test is that first one. And yeah, I think, all of these have, it's hard for me to really pick one. Marisa, what do you think?
Yeah, my mind is turning. Part of me is thinking about how, so if we're not in the Anthropocene, we're in the Holocene, as we found out from my cup. And isn't the Holocene also denoted by a presence of human change and impact? Isn't that one of the factors of how we describe 11,700 years ago?
Go ahead, Graham. It looks like you have
Well, you've got my mind turning as well. It does. And so I don't have anything terribly substantive to say, but this is part of where the controversy comes from. Is there's some folks who say, no, we got to leave humans out of it. There's some folks who say, oh, most definitely we are in the Anthropocene. And other folks who say, this is a bit of a silly argument. This is all just a matter of, what we're calling the same period of time. And so it is kind of a tricky conundrum of we're trying to, reshape sort of reshape this way that we think about, the last 100 to 10,000 years. What were you going to say, Gavin?
Well, I actually think that is important because when we're building a geologic timescale, we're looking at times where the Earth is changing. And I think that it's important to acknowledge the changes in the Earth that humans are making, and not so much the changes that we've made throughout human history. Because if you look back, if you didn't have fossils and things, you wouldn't know that humans were around. But for the past around 100 years, where we are literally changing the chemistry of the environment, and that's going to have and has had lasting changes throughout Earth's history and throughout the Earth system. And so I actually am a proponent of the Anthropocene because it does sort of acknowledge how humans are changing the Earth, which is in and of itself changing, but is, if you mark it by a timeline, I would say, or a point in time, I would say I would mark it at the Industrial Revolution.
And yeah, that also, so what I'm thinking about these three events that you guys have presented here, seems like nuclear explosions are kind of static events that have long lasting effects maybe, or that like they might punctuate a rock record, but they may not have effects that go on for thousands, tens of thousands, millions of years. Whereas the systems of impacting climate may have impacts that are longer lasting. And so when we decide how to mark these periods of time, it seems to me like all of the things that you guys have brought up thus far today, maybe there has been major impact events like a major meteor, but it seems in general it's about something going into motion, and sometimes over a long period of time, that has a long impact. And so it also seems like it's hard to know if we're in it right now what that long impact would be. So is that part of the argument too, that people are saying that it's just too soon to know, and that while it may very well be that we have now entered it, we can't know until tens of thousands of years have gone by?
I would say you hit the nail on the head, and that's really the crux of the argument. And that you're right. The things that we look back on in the rock record are events that have changed in a large way, and really only time will tell. But it is an interesting thought exercise, I would say.
It is. Yeah, this has been fun. And I like this idea of that, with the geologic time scale, we have the benefit of hindsight to be able to say, this was a key, period of time. This was a key block of time. And now we're kind of right in the midst of it. So, sussing out what the boundaries of it are, it's some new, brave new territory.
That's right. That's right.
This is fun talking about. And also, I don't know if I've been drinking enough water today, but we have gone from the Holocene down into the Cretaceous.
Okay.
Pretty exciting.
Yeah.
Lots going on in the Cretaceous.
Totally.
Yeah. As we discussed. So what are we going to be talking about next week, guys?
Yeah, so next week we're going to be talking about these great points in time and how we know when they happen.
That's right. How do we actually put those points on the timeline? How do we measure the time?
Okay, cool. The tools of the trade.
That's right.
Wonderful. Well, thanks everyone for joining us, and thanks Gavin and Graham for taking us through the Earth's greatest hits. Looking forward to learning more about geologic time next week.
We are as well. Thanks, Marisa.